And we started optimization. And I started out with showing you, when you got constraints written out by equations, how do you think about it? We talked about, tangent space to vectors that change nothing. And then we eventually find out if you want to have a local minima or a local maxima, your objective function is f here. The constraints are given by equations h1, h2. This first sheet is where h1 equals 0. Second sheet is where h2 equals 0. H1 here is this little guy, that guy right there. Then we find out eventually if you want to have a local min or max, the gradient of your objective should be expressed in terms of the gradients of defining equations. Right. So what was the reason? Because in that case, your gradient becomes normal, orthogonal to all tangent vectors. That means none of those tangent vectors will make a change. That means there's nothing better you could do. You're at like a locally optimum point. Okay. So to write it more like algebraically, let me see where did we write it? Yes. So here is the algebraic version of it. So if your x star is an optimal point, the gradient at that x star should be expressed as combination of gradients of defining equations. And if there is no defining equation at all, if there is no constraint, then there is nothing on the right-hand side. It's just literally 0. Right? So if you're trying to optimize over, say, the entire Rn, then there is no h, right? So it's like everything. Then that means the gradient has to vanish in that case. Okay. All right. And then we also got the second order. We did some examples of this, and then we also got the second order condition. So these are necessary conditions. This means that when you satisfy these, it doesn't mean that you're actually optimal, but to be optimal, you have to have this. Okay, that's necessary, doesn't mean sufficient, right? Okay. So first order necessary means the thing with the gradient. Second order means the thing with the Hessian. And the Hessian is take one more derivative. Gradient was a vector. If you take one more derivative, if you write them all together, it's going to give you a matrix, right? That's what we call a Hessian matrix. This nabla squared fx, that's what it means. And the second order necessary condition is the following. When you write down your Hessian, if you take any tangent vector, when you multiply it from left and right, you will get a number. That number has to be non-negative. And why? It's quite intuitive. If you look through Taylor expansion, this is your Taylor. And then first order necessary condition says this has got to be 0. My gradient has to be orthogonal to every tangent vector. So this is 0. So this is what I got. And I'm trying to have, say, this guy being local min. That means everyone else should be bigger. And that means like this guy's got to be a positive number, or at least 0. So that's why. So Hessian should behave like a positive matrix in the local neighborhood of your point, if you want it to be local minimum. If you want it to be local max, the other way around. Hessian should become negative. If you want local max, you want this guy to be bigger than everything else, so you want it to be negative. Right. Okay, so this was first and second order conditions. We also talked about convex stuff and then descent idea and started setting up gradient descent. We'll go back to gradient descent and do more of it today. Before we do those, let me show you a little digression, which is, I think, useful and important to know. Yes, so I'll show you a version of this necessary conditions when the domain you're optimizing over is convex, okay? Sometimes I got an equation defining the stuff, then we know the gradients and whatnot. Sometimes you just have a shape, you don't necessarily have the equation. Okay? Depends on how your problem is set up. And among those shapes, the nicest ones for optimization are convex shapes. What was convex? You take 2 points, take the line segment between, that's got to stay inside your shape. That's a convex shape, right? For example, this is not a convex shape. You can take a dot here and a dot here, the line segment will go out. I did not touch, you can still take. Okay, so let's say I got like a convex shape. So and I don't want to use the equations. I don't have them. So can I still talk about this like normals and, you know, necessary conditions, whatnot? Okay. So this is my convex domain. Now you take a point on that convex domain. We define this thing called normal cone. What is it? You take any other point inside the domain, you look at their difference, and your vector should give you a negative number when you dot product it with the difference. So let me try to draw. So let's say, so I was drawing it for something on the boundary, but you don't have to be at the boundary. Let's say this is your x. Now you get to pick any direction y. Pick any of them. And then you need somebody, when you do the difference, difference is y minus x now, right? This is this guy. Your vector is got to be negative for every such direction, right? So now if I found a point, say, in the middle of that shape, if you think about all the directions, can you find anybody that is like giving you a negative number when you multiply it with all that possible directions? Probably not. If this thing is full dimensional, you know, think about like a ball, take the point in the middle, think about all the directions you can create everything basically. So you'll not find any V in that case, okay? So you can define it anywhere. Usually it makes sense at the boundary. That's what I'm trying to say. But sometimes your convex shape is included in a smaller place. Let's say if my convex shape was something like a ball sitting in a plane, then even if you give me somebody in the middle, I could go find some V that is orthogonal to every single direction. Sometimes that happens. In optimization, your shape being full dimensional or not matters a lot, but you don't always know it. Okay, that's also another subtle point. Sometimes it's visible from your problem, sometimes it's not. You have to somehow think about, if I literally have something full dimensional, or is it living like a smaller place? Okay, yeah, and this changes a lot for your algorithms also. Okay, anyway, so this is your cone, and for the boundary guy, the cone looks like this. Why? Now you think about, this is your point. Think about all the vectors you could draw. Now you could find somebody V whenever you take any such direction. When you do V with it, you will get a negative number. Let me try to draw, so maybe it becomes more visual. Let's say this is my X, and pick any Y here, anyone. Draw the vector. Okay. And now you want some V that is gonna be negative when you dot product with any of those vectors. For example, if you take this V right here, it will do the trick. Or anybody inside this cone, basically, right here, this whole cone will do that trick, okay? So why am I telling you all this? Because in this case, your necessary condition becomes the following. If you want a point on the boundary to be a local min, then you need negative of your gradient to be inside that cone. Okay, so this is literally behaving like the normals we got, but in those normals I was able to combine them as any way I like. First gradient times a number, second gradient times a number, and I could write my gradient that way. I was good, right? So here you're not necessarily writing any whatever combination. You're looking at a particular cone. It's more restrictive. Okay. So later we will use this for some algorithms. Not today, probably next week. But this is just trying to tell you this first order necessary conditions exist in a setting where you don't necessarily have to have the equations. That's basically, for the moment, all you need to get. And for convex shapes, it literally becomes like a cone. And sometimes in engineering, they call it the descent cone. It's the normal cone. And then the first order necessary condition literally is like, look up the gradient, negative of it should be inside this cone. Okay, right? Okay, now let's get back to our gradient descent discussion. Any questions about this? As I said, you don't need to deeply understand everything here for the moment, but just a point of, first order necessary condition being more general than what I just showed you last lecture. In a way. Yes, go ahead.
Is it
in a way, yeah. That's a very good intuition. Yeah. So I'm like at a dot on the boundary. Yes. And depending on your dot, the cone will change. Very true. So let's say, since you ask, let's say my convex shape was a square, right? This doesn't look like a square, but suppose it is. So for curve intuition. So in here, there is no curve at all, right? It's just straight. So the normal cone becomes just like single one direction. But when you get to the corner, it's curving now. The normal cone becomes like a 2D shape. Exactly. So it's a notion of how curvy the thing is, and your gradient should capture that so that it becomes an optimal point potentially. Very good. Thank you. Very good intuition. Yeah. All right. Now let's get back to our descent discussion. So I'll probably just put one exercise about this today on Canvas, so you at least get to visit the definition again and do one quick exercise so you retain it. That's about it. So let's go back to our descent discussion. So what was descent? You are gonna find the direction V, and if you go in that direction small amount, your function should be decreased. That's a very intuitive definition. But here the subtlety is this definition only holds for small amount. If I push that t too much, if I go in that direction a lot, I might be increasing my function. Okay, so we're only looking at very local, like a one small perturbation type perspective. Okay, and then we talked about like what kind of directions are descent. Not surprisingly, it's determined by the gradient. You look at directions V, where the gradient dot product is going to be a negative number. These are descent because just think about Taylor. First term in Taylor is going to come out this way, and you want it to be negative, so you're like locally for very small perturbation decreasing. Okay. And then here is your gradient descent algorithm. Okay, let me fix this. This should be subscript, not script. The update rule for gradient descent is you're at a point xk, and assuming now we are doing unconstrained optimization, we will think about constrained versions of this later. I'm at a point xk. My update rule is very simple. Take your gradient, minus it, and then put the number here, update. Okay. Why it is called gradient descent? If you pick that alpha k right, this should be descending. Because minus gradient, of course, when you take inner product with itself, it's going to be a negative number. So this gradient, minus gradient is a descent direction for sure. And I'm going in that direction. If I go small enough, I'm good. But if I push my learning rate too much, I might even increase my function. Okay. So if you pick the learning rate right, this will give you a decrease. And if you keep decreasing, eventually you will arrive to a local min. That's the idea in gradient descent. Okay. Now, you got two immediate questions. How many steps I should do before I hope to converge? And how do I pick that learning rate? And one thing that you can start thinking about now, and it will keep coming back whenever you do an optimization thing, is like, let's say this was my local min, right? And I'm at a point, I'm not far. Say this was, say, x10, right? And I'm doing a gradient. Now, if my learning rate is bigger than the difference between them, my next one will probably might be even further out than the local min that I was before, right? And you could keep zigzagging back and down. And that actually happens. So the learning rate, somehow you need to have a notion of how close I am to the optima, so that if I'm close, maybe I should start having smaller steps. So eventually I hope to converge. Okay. But if you're like if you would know a lot more, let's say you know everything, suppose, for a sec, and your thing is like close to a local min, but it's not global min. In this case, you don't want it to converge. Then if you would know all these, then you would make the step size bigger. So you just get out of it and you keep going to the global min, right? So what I'm trying to point out is it's not entirely trivial to pick what's the correct learning rate at a certain step in your optimization process. Okay. And learning rate is the machine learning name for this number right here. So it's literally just a number. Okay. So before machine learning took over the world, probably it was called something else. I forgot what was the name in optimization before. Okay. So, all right. So let's get going. So now we will try to get some guarantees for nice functions that we know some stuff about. So here your f is your objective function. Either it's your loss or your reward in your optimization scheme. For some functions, we can actually do principled ways of picking this learning rate, and we can actually prove rigorous estimates. Okay, but I'm not going to claim, the type of functions we are able to handle mathematically is going to be the functions you will see in the wild. Okay, so usually the stuff you work with does not necessarily satisfy all the assumptions you need to do rigorous math. But what you do becomes like a laboratory. So you prove some stuff for nice functions, then you try to tweak it so that it also works for your functions in the wild. If you have no idea even for nice functions, then who knows what your algorithms do. That's the main idea. So, okay. All right. So like we would call a function Lipschitz if the change in that function is not so abrupt. What does that mean? I go from fx to fy, and the change is bounded by how much difference was in x and y times a number L. Okay. So let's say times a number 100, times a number 10. That means if I'm going from here to a little bit, the function is changing at most 100 times that difference. So the function is not terribly abrupt. That's what it means. Okay. And you could know this if your function has like a gradient. The gradient captures how much changes is happening in your function, right? That's the meaning of it. So if your gradient is always, so I'll get to this, give me a sec. So this is L-Lipschitz, and that'll be L-Smooth. I'm still talking about L-Lipschitz. Don't read the second part. So how would you know L-Lipschitz? Well, if your gradient is always having norm less than that number, then you know your function is L-Lipschitz, okay? So, and where does your gradient should be behaving nice? This was your point X, and you want to point Y. Just look at the line segment between. On that line segment, norm of the gradients should be bounded by a number. That's what you need. It could be going crazy somewhere here and there. It doesn't affect you for this definition. If you're only looking from, I'm going from X to Y, what happens in between? Okay. So in general, if you know your gradient is always bounded by a number in the entire domain, then you know it behaves nice in the entire domain. So that's the L-Lipschitz thing. And then there is another notion called L-Smooth. This is now about the change in the gradient. Yes. Take anything discrete. So like switching systems that you have seen in engineering, right? So it's going, say, like 0, 0, 0, all of a sudden it became 1. Yeah. So discrete stuff would not, well, you might still push discrete to do this maybe, but not really, right? So no, okay, yeah, discrete would be anything that doesn't have that gradient controlled is a candidate. If you have huge gradients, then things can go crazy. Like, for example, current funding scheme in United States is not Lipschitz. Every day we have to check what happened and then see if we still have the grants. All right, next thing is like L-Smooth. What is it? Now you're talking about the change in the gradient, not in the function. It's one more step, one more piece of information. So this means your function is not only Lipschitz, the change in the change is also bounded. It's behaving kind of quite nicely and smoothly. Okay. All right. So again, this time, if you want to know this L-Smooth thingy, then you need to go for the derivative of the derivative, which is Hessian. Okay. So you need to now bound how much change is happening in the gradient, not in the function. Now, do you know that? Look at the Hessian matrix. Okay. It should be the biggest singular value. Should be at most that number L, and the smallest one should be at least minus L. So if your Hessian is like behaving nice between, say, 100 times the identity to the minus 100 times the identity, then that means your function is smooth in this sense, okay? All right. And for this kind of functions, we can handle what gradient descent does to them. So, so first thing is like from smoothness, you get a bound when you travel from X to Y. So you know Fy is less than this. And how do you do it? Again, you just do Taylor, okay? So that's the first thing you know when the thing is L smooth. So basically it behaves as if I was just going from X in the direction of the gradient Y minus X much. Now I might be missing at most that number L times the distance squared divided by 2, okay? And if distance is not too big, square is even smaller if it is less than 1, yeah. And then you also have a divided by 2, and off of it, now you start picking your learning rates. Okay, let me show you how that works. So, so you do that. So I'll show you all the math. You know, it's unless you have a photographic memory, it's near impossible to remember all the equations you see back to back. So if you don't remember everything, don't be, you know, upset with yourself. That's very normal. You need to try to follow the main idea of how these things are working out, right? So if you try to literally follow line by line, I don't know, at least to me, it's usually near impossible. When I listen to talk giving line by line math, I just try to see what's the main idea. And if you want to see the lines, I go back, look at that writing or recording. And some people are different. I worked with people who can just start and write down 2 hours of equations, but this is rare. So, all right. So let's see, what do? We use that lemma that I showed you for L smooth stuff. Now, what is my update? I'm going from xk. This was my x. This is going to be my y. And y minus x is this thing right here. This is my update. So you'll write down first the thing that we had right there, this lemma. This is less than blah, blah. You write it up. And it gives you something like this. And then what's next? You try to clean it up. If you have a number here, norm squared, number gets out as squared. And then what else we got? Then this times that is nothing but the norm of that vector. You know, this is what you got now, directly applying your lemma. Then what you do, you look at it. You say, my next point, my previous point minus learning rate times how big was my gradient, squared, norm, plus I might be losing this much in my estimate. So if you make that learning rate a little small, then this minus will win over the plus. You'll keep going down, and that's what you want to arrive to local min. So that's the idea. So what you're going to do, you're going to pick this learning rate. You can pick, if you want, fixed like 1 over this thing, 1 over L, say. Okay? So let me write down, in the case you pick it 1 over L. In the case you go pick this as 1 over L, this is how it looks like. Now you know at every step, you're decreasing at least this much. Now, if this is your learning rate, you're guaranteed to descend, okay? So remember, the descent idea was all about, I find a direction. If I'm going small enough, I'm decreasing. If I'm going too much, I may be not decreasing. So I need to strike a balance. This is being conservative, just looking at the math and saying, if I would just go pick 1 over L, it works fine, okay? And then based off of this fixed and conservative learning rate, you can prove estimates. Basically, you iterate this inequality starting from your x0 until the number of steps you did, okay? And then you iterate and sum up. So what's going to happen if you iterate and sum up? It's going to tell you, okay, let me see, why did I write it this way? Probably I did a mistake right there. So this should be probably xt. This should be x0. Yes, right? So at every step, I'm decreasing by minus 1 over 2L times this quantity. So eventually I'll be decreasing at least this much when I do t steps. And in other words, if you, again, yeah, I again wrote that wrong. Let me fix it. If you move things around, you end up saying the summation of all that gradient stuff is at most the change in my function times that number. Okay. And then that change, even if this would be the smallest, that change is at most this. And then you end up saying one of those, if the summation of t of them is at most this, the minimal among them is this divided by t. Okay. So if I went 100 steps, there should be some gradient, which is less than, say, the biggest thing your function could take, minus the smallest that you're shooting for, divided by the number of steps times that number. So you see, we still did not prove a full convergence thing yet. We just know now, along the way somewhere, gradient is almost going to vanish. And that's what I'm looking for. But it might be going smaller and bigger. We still did not solve that issue. Okay? Because all we assumed is like function has some smoothness. We did not assume it's convex, it's nice. We just said, okay, second derivatives are behaving nice for this function. And this is what you're able to prove off of it. You say, if I iterate the gradient, I will even, let's say 100 steps. One of those will have a, if I iterate the gradient descent 100 steps, one of those steps will have a very small gradient, the thing divided by 100. If you iterate it, usually 100 is very small, you know. When you're running whatever packet you're using, you get to pick the maximum iteration, right? I don't think I pick anything less than 1,000, usually 1,000, 10,000, 20,000. If you get a GPU, much more, you know. So that's how you should think about this. So you do a lot of steps, you're kind of searching for a small gradient, and you know your gradient descent will visit one of those. And you can also put it like a manual if condition, right? So keep iterating unless my gradient was small. At every step, you can evaluate the gradient, and you say, if it is less than some very small epsilon, just stop if you want. That's up to you. It may be wise or maybe not. Anyway, so that's what you can prove only with the smoothness assumption. And if we assume convexity, then we can prove actually what we want. If we assume it's also convex, then we can show the value at the tth step of the function is actually, this is the optimal global min I'm looking for. The difference between where I am versus where I really want to go is at most where I started off minus the optimal thing, the distance between them, divided by number of steps. Okay, so literally you start your point algorithm at an initial x naught, right? And you want to go for the local min, and you keep iterating. If your thing is convex, and if you just fix the learning rate, this 1 over L, you know the distance is always getting smaller and smaller, and the rate that it gets smaller is bounded just like this. And you know, so if you got lucky, your initial wasn't too far from local min. After a good certain number of steps, the distance will be already very small. Let's say if you know you're on a bounded domain, let's say I'm optimizing on the spare. If I'm at a point, what could be the longest distance from the minima? It could be like North Pole versus South Pole 2, right? So if you're already in such a situation, you know this is less than a number, then if you want, I want to stop when my distance is less than epsilon to the min, then you need to make this guy 1 over number of steps less than your epsilon. Does it make sense? So you will decide your own guarantees. Let's say you want to stop when the distance of where you are in terms of your function number minus the local min is less than 1 over 1,000. And if you knew your thing was at most 2, then here you need to go like 1,000 steps. So you get to decide what is good enough for you. And then this immediately gives you a bound for the number of steps. Then you mathematically know how much iteration is good enough. Okay? And this is the case when your function is convex. And since we are using also this derivatives and stuff, we also assume it's differentiable. So for example, if you're using an L2 norm, right, that's convex and differentiable. So let me write down some functions you have seen before in this class and elsewhere that are fitting into this bill. So for example, we have done this TCA linear regression, logistic regression, right? And there, what was the loss function? You remember? It was usually something like this. My function f spits out something for my data xi, and I got some label yi, and I got a square. Okay. For example, this would probably be convex and differentiable. And sometimes we also add some penalty next to it. We say like lambda times, so this f is having some parameters theta. Sometimes we say lambda times L2 norm squared as regularization parameter. This is still convex and differentiable, okay? But if you add L1 norm instead of L2, then you lose differentiability here. It's still convex, but it doesn't satisfy your assumption of like you always get a gradient or you always get a Hessian. Why? Because L1 is something about absolute value, right? An absolute value plot looks like this, and here that's not going to be differentiable. So L1 is not necessarily satisfying all the assumptions we have. L2 does. And if you're adding L2 to something still that's looking like L2 and whatnot, that still satisfies. So for example, if you're running your gradient descent for doing linear regression, logistic regression, etc., you're likely safe. But if you're running your gradient descent for a gigantic neural net with some customized loss function, the theorem will not tell you any guarantees, but you hope that it will behave as if you had the guarantees. Okay, that's kind of how it usually goes. All right. And why in convexity we can prove a bound? I'll just tell you the main thing. So in convexity, we got two things. So this is for anything that is L-smooth. But for convex, we have one more, which is take any point. If you take another point, go in the direction and multiply it with the gradient. Remember, a definition of convexity was it was always staying above, right? So, and this is correct for any point. I picked the local min. That's because it's useful for me, but you could pick any y and x. So a definition or a version of convexity, let me remind you that thing. Seems like not everybody's remembering that from the faces. So let's, yeah, here it is. So this is what I'm just saying. For convex, you also have this one. If you're at a point, go in the gradient direction, your function always stays above. Okay. So since we have also this one on top of the other one, you combine those and you end up proving guarantees. That's the main reason where we're able to handle convex stuff. So let me go back. Yeah. For convex, we have this and also that. Okay. And we will combine those and analyze. And you might be wondering, why am I showing you all this technicality? Because main motivation for me today is we will soon start talking about stochastic gradient descent. And that's the workhorse algorithm in anything that goes with machine learning and data science. And there, to have an idea of how stochastic gradient might work and why it might be working, we need to have an intuition about how this type of stuff is analyzed. That's why I'm showing you, not only to show you a proof, because the intuition from here is useful when you design stochastic gradient descent. Okay, so bear with me a couple of minutes. That's my motivation. You might also want to actually learn. That's also another motivation. Learn how it is proved. You'll also get it here if you bear with me a couple of minutes. So we got this from this L-smooth inequality, and we got this because my function is convex. And then when I combine these two, what do I get? Next one is less than fxk minus this, right? And for fxk, I also have an inequality. That guy is less than the best. This went to the left. And when it goes to the left, this swaps. And this is literally what I wrote. So instead of fxk in this inequality, I am writing the bound I get out of convexity. Okay, so that's my first thing. And the second thing is there's a little algebraic trick that comes out super useful. So this was my update rule: xk plus 1, xk minus this thing. So forget about this for the moment. This is my update rule, right? This is how I define the gradient descent. Now I'm going to relate this update rule to the algebra I was seeing off of those inequalities, okay? When you do the algebra, it comes out as the norm squared of the left is norm squared of this guy plus this minus that. So when you look at norm differences of this and that, literally you get an expression that looks almost like your inequality here, okay? So that way you're able to relate the change in your function to the distance you're traveling. Right. And that comes out as the algebra here. If you clean it up, it looks exactly like this. The gradient times this one minus the change that we know is literally the same as look at my xk plus 1, how far it was from the local min, minus where I was, and multiplied with that number you got. And when you plug that into our previous estimate, everything cancels out and you got you get exactly this one right here. Let me walk you through. You basically take what I wrote there, keep writing it in the sum, all the inequalities. And then since you see this is going to cancel each other, x2 minus x star, x1, then in the next it will be x3 minus x2. There will be a whole bunch of canceling. So when you sum it up, it comes out super nice. What you get on at the end is this. I started somewhere at x0. I keep iterating, and I'm summing up how far I am from the optimal point. Okay, that sum is less than equal to literally the last thing, everything else canceled, times your number L divided by 2. Okay, and then you divide everybody by number of steps you did to get like an average notion. Okay, and then your minima should be, of course, less than the average stuff. I'm always decreasing along the way. I am guaranteed to decrease because function is smooth and nice and whatnot. So average is here, and that average is less than this thing plus the smallest it could be. So at the end of the day, what you know, where you are after t iteration is less than equal to the best plus your distance divided by the number of steps. And usually distance is hard to control. You just need to have an idea like how big is your domain or where you started off, how far is it from your potential minima. So that's why either you have a bounded domain or you have a good initialization strategy. Okay, so this you need to somehow control without math, and then you immediately know how many steps you need to go until this is small enough. Okay, so the version you would see in textbooks and stuff would look like this. If you want this difference to be less than epsilon, make that bound L divided up number of steps, blah, blah, less than epsilon. That means your number of steps should be bigger than whatever this divided by the epsilon, okay? If you want to be less than 1/1000, your number of steps should be bigger than 1000 times whatever this distance is times your L, basically. Okay. So that's how it comes out. And if you have even more, if your function is not only convex, but strongly convex, then you can say a lot more. It converges much quicker. You immediately go from linearish to logarithmic. So strongly convex, we could prove a lot more. What is strongly convex? L2 norm is strongly convex, for example. So what was the definition of strongly convex? The definition of convexity, those inequalities, they should be strict. That's what strictly convex means, okay? And in those cases, the niceness is like strictly convex have, as we talked, global local min, just a unique point. And you kind of end up converging, it goes there pretty quickly, okay? So this strongly convex is too much to ask for any application usually. Okay, so far what we did, if you don't know anything about your function, it's very hard to pick a good learning rate. If you know it is L smooth, you can pick 1 over L and get estimates. If you know it is L smooth and convex, you get very legit estimates. That's what we have done so far. Okay. Yes. So if you're looking at the Hessian, highest singular value will be L. That's right. For L smooth. For L Lipschitz, you literally look at the gradient. How big is the norm of that vector? Is your L. Yeah, exactly. It's very good. Fantastic. And for strongly convex, the Hessian biggest will be your L, but the smallest will be bigger than 0. Hessian will never vanish in strongly convex stuff. And that smallest singular value will be this M right here. And using that, you prove a lot more for that kind of stuff. Yeah. So very good intuition. All the smoothness stuff we are talking about is literally look at the Hessian matrix, look at the biggest eigenvalue, smallest eigenvalue, how that goes. If it is always bigger than 0, smallest eigenvalue, it's like a strictly convex guy. If it is sometimes 0, that may be convex. If it also becomes negative, the eigenvalues, then you lose convexity. Convex is related to something positive, always. Okay, now we are done with all this math. Now, how are we going to actually write down a descent algorithm, right? I have seen math works out in like very nice functions. Yeah, right. So X star was the thing we are looking for and we don't know. Yeah, so X star is the optimal vector that we are shooting for. We don't know what that is. We just write it this way to be able to handle what's going on, because eventually I want to know how far I am when I put my num vector inside my F compared to where I really want to be. So that X star, I don't know what that is. It's just like a placeholder for me. This is where I want to go. If I knew, I don't need to run any algorithm. Right? That's where I want to go. It's just like a placeholder in the estimates. So you don't need to worry about it too much. So the main thing is like gradient times that vector, the difference from where I am versus where I want to go. That is bounded. That satisfies this particular identity in the second one. So if you really want to go through in your head, these two things are what you need. So this one and that one, and combining them gives you the entire proof. Okay, but you don't need to go through all this on top of that. So what I would say is, if you want to keep some intuition in your mind, this is coming only from L smoothness. And this guarantees when I pick my learning rate as 1 over L, I always descent. That's what it is. This is what this is saying. And when I know convexity, I know a little more. Okay. When I know convexity, I know a little more than what I just said. And you plug in all that stuff, do the algebra, you end up getting the estimate I just showed. Okay. And the only reason I showed you guys that stuff is eventually we will get rid of deterministic gradient descent. We will try to do probabilistic, stochastic gradient descent. And you will try to carry over that kind of intuition to probabilistic world, basically. Okay. Now let's get back to more like algorithmic discussion. So, okay, I saw like if I can find such a nice function, if I do all the L smoothness right and pick my learning rate 1 over L, I got some estimates. Cool. But probably that's not what I will always see when I try to solve something. So how do I write down an algorithm and implement it? I want to write a descent algorithm. So basic update rule is something like this. You have a direction, descent direction vk, and a learning rate alpha k. Right? You're at that point. This is your update. And what we want to know what's a good vector, what's a good learning rate. Okay. Okay. So one intuition we want is like when I do one step, I want to have a decrease like I was having in that smooth and nice case. I was saying at every step, I'm decreasing at least 1 over L times the norm of the gradient. We had that L smooth inequality. That's the intuition we want to keep having. In this case, or also in the probabilistic case. Okay, so how do I find that vector vk? So what do you want from that vector? So if you write it mathy way, you don't try to go through this. I'll explain you what that is. What you want is that vector should behave like the gradient. So if you have the function f, and if you can just take the derivative, okay, take the minus gradient as your descent direction, you're fine, okay? But if that's not the case, or if you don't want to compute all that gradient, if it is too many number of variables, think about you have like a million variables. Computing the gradient vector will take a long time, okay? So we don't want to do that. We want to have some sort of vector v that we can compute quickly. In terms of how big it is, it's not too different from how big would be gradient vector if I compute it entirely, okay? Like two numbers there, their norms should be comparable. What else I want? What I want is like when I would take the negative gradient, multiply with that direction, and this should be not too small. It should be bigger than at least some sort of epsilon, so that I am at least decreasing epsilon much at every step. You know, it's a descent direction, but when I go in that direction, the decrease is too small, you will not see so much improvement. So intuitively, that's what you want for this direction to do for you. And people have been coming up with ways to do this since ancient times. Who knows, maybe Gilgamesh had a way of gradient descent, okay? So people have been doing this for a long time, right? So one thing that is attributed to Gauss and Southwell is like, if I have an idea about my function, if it is very particular, I can just go try to pick the coordinate of the gradient, which was the biggest. Somehow this only works for very specific functions. So when they were dealing with stuff by hand, their functions were like not so complicated. So they have an idea of like the gradient is a huge vector, but some of the coordinates are dominant. They just try to find that coordinate. Let's say it is the 100th coordinate, very dominant. Then just write a vector. Everywhere it is 0, only in the 100th coordinate, it's putting that big number. That's the change, okay? This only works out if you know function very well. But funny enough, we will imitate this in probabilistic world. It will start working. Okay, so second idea is like randomize. So what you do, you don't want to compute all that gradient vector. It's got like a million variables in it. 1 to n, let's say n is a million. Pick one of them randomly. Just one single coordinate. Just compute that coordinate of the gradient, one partial derivative. Do like Gauss was doing. Just put that partial derivative in that coordinate. Everything else 0. Minus in front, that's your descent direction. Okay. And this is, why do you know this is not a terrible idea? Because since it is probabilistic, you can prove expectations. You can show at least you will get 1 over the number of coordinates worst case loss. So at least you know it is doing something that you would like it to do. This might be the worst loss you're having, okay? And this is like picking the very bad coordinates. This is a very conservative estimate. So you're randomly picking a coordinate, among your gradient coordinates. If you're not too unlucky, you will at least pick like an average one. Okay, and since it is hopefully totally random, creating random bits is a completely different discussion. It's interesting, but I'll not get into it. Suppose your Python library is able to emulate this very well. You are able to pick a random integer. Then you don't expect to be that unlucky because you're picking it totally randomly. So it's not a terrible idea, basically. May not be the best, but still pretty good. Another approach is like, maybe don't be that lazy, still be lazy, but a little less lazy. What do I mean by that? Don't literally go pick a coordinate of the gradient. Create some cheap vector you could compute. It's going to be random. This is your random variable. This is your point x. What you want from it is like, in expectation, it should be looking like your gradient. This might look abstract now. I'll give you examples soon, okay? And then just use that vector for your gradient descent. So the second idea is like, maybe just picking one coordinate is too lazy. I'll do a little more work. I'll create some random vectors where I know in expectation it is exactly the gradient I want it to have. But since it's created randomly, hopefully it's going to be much easier to compute. Let's say it's going to involve 100 coordinates instead of a million. Yeah. All right. That's the second idea. We will go through this in more detail. This is how to find a vector. Gauss randomize with a little more work. Now the step length condition strategies. The first discussion was about finding a descent vector. Now we need to talk about the learning rate part. You can fix a learning rate. That's called fixed step length or fixed learning rate. You can also do other heuristics. Any packet would have linear decay in learning rate, exponential decay in learning rate, and fixed learning rate. Okay, and people are not shy to give a machine learning talk and say the best learning rate was 0.0.3. How on earth Okay, so that happens almost like every 2 machine learning seminar you listen, something like that can happen. Okay, so these are like 3 standard heuristics in any package. You could fix a number you like, you could decay it linearly or exponentially. Okay, and then second one, if you want to be doing more work and if it is feasible, you can do what's called exact line search. What is it? I picked my descent direction, and this is where I was. I'm going in that direction now. I want to pick the best step size, best learning rate for this particular step. What you do, if it is possible, you can look through. This is literally now a line, right? So I was at xk, and I'm going in direction vk. If you think about it as a whole, if you could go as much as you want, what would it be? It would become a line, right? So that's why it's called the line search. If your function is simple enough, this is not too expensive to run. This is rare though. You can literally go find the best step size at every single step. That means that every single step you're running an optimization scheme in it already. Okay, so already in gradient descent there is one another optimization algorithm, right? Can you do this? Well, it depends, right? So there was a paper just like a couple months ago. They were claiming they could do something like that for multivariate polynomials with up to a good degree. So sometimes people can manage, but you don't usually expect this to happen. But if you're like an electrical engineer, probably you have seen something called model predictive control. Or if you're a reinforcement learning person, that's what you do all the time in that stuff, okay? So this is not completely crazy. Okay. The third one is what's called approximate line search. So again, a whole bunch of math popped up. Sorry for that. So people try to come up with like cheap conditions where you check it, it guarantees the vector and the step length behaves as you want them to behave. Okay, so it's not like the best thing you could find of, but at least it guarantees at every iteration your function is decreasing at least some number of much. So every step does something this way. And there is plenty of those conditions people come up with since 1960s. One of the thing you would see very commonly is called Wolf conditions. Then there is like Goldstein conditions. There's a whole bunch. Okay, these are all implemented. This is basically trying to imitate that line search, but not do it. Just try to come up with a condition that tries to behave like an exact line search. So what is it? You want this to be less than this much, and this to be, so this guarantees you're decreasing at least this much, okay? And this guarantees your step size is not huge. And you come up with some predicates that make sure this is satisfied, and you run with that. And that predicates also can get expensive. Then, if that's the case, you resort back to the trick that every computer scientist learns in grade school, bisection, right? So you keep dividing to 2 or dividing to 5, or binary search, what we learned binary search, right? So it's like, that's the good old idea. So I don't know what's the good thing to pick. So what do I do? I pick an initial guess for my step size, and I pick a number. If I'm dividing by 2, this is going to be half. This is the default in these implementations. You can make it bigger if you're more adventurous, 1/4, 1/10, 1/8, whatever, right? And every step, I'm checking if this satisfied the conditions I wanted to satisfy. If it is satisfied, done, great. If not, take half of it, check again. You check until the conditions you wanted in the previous step is satisfied. When they're satisfied, done. Okay? There's a standard binary search idea. It's called backtracking the line search in optimization literature. At every step, you let your algorithm have a guess and keep halving it, or maybe keep dividing by 5, unless it satisfies the approximate line search conditions. Yeah. So these are general strategies that people have been doing for a long time to come up with decent algorithms. And I'll try to show you the more modern versions that you would also see in PyTorch soon. Any questions? Yes. Yes, exactly. When you know that L, you don't need to do any of that stuff. You just pick 1 over L. So the reason we are doing all this is we usually don't know that L. So we first do the math. If we know the L, how it is going to look like? Very good question. So why did we do all that math? Because suppose if you knew that, for some functions you might know actually, then you have the theorems and math that tells you, okay, just pick 1 over L, you're good. Okay. But usually we don't. So we say, okay, let's create algorithms that would behave like that theorem for us. We are trying to first pick a descent direction without computing the whole gradient. That was the first part of discussion. Then second, we are trying to pick a learning rate, which would behave nice like those theorems. Very good question. If you know the L, it's good. You already have a baseline. Pick 1 over L, it's going to work. And if you improve, you can find better learning rates by some experimentation, even better. Right? Okay. So that's all for this gradient descent type discussion. Let's start stochastic version of it. Any questions? I'll probably tell you stochastic gradient descent and some modifications today. Maybe I'll explain a little more next time, maybe first 15 minutes of next lecture, why this is actually working. Okay, stochastic gradient descent, the workhorse algorithm that we all use all the time. How does it look? I got some data points and say I got some labels. This is my loss function. And I would like to actually compute the gradient and do some gradient descent. But since you got 1 million of those parameters, these days maybe billion and even 1 trillion, you don't want to compute all that gradient. You want to do something quicker, but also still does a reasonable update. Okay, so one idea is this. As I said, create a function that is random, this G. Theta is your random variable here. Theta could be a coin flip. It could be a Gaussian, whatever randomness you would like to utilize. What you want is, in expectation, that function should behave like your f. And if you don't like this, even the second one alone is good enough. You need somebody. When I take the gradient, it behaves like the gradient I actually wanted to compute on expectation. Okay? Then I'll use that cheap random function as my update rule. At every step, I'll just toss my coin, compute that cheap guy, update. Okay? So some examples of this. Here's the first example. This is like the linear regression type stuff. So this is your data. This is a vector, right? And then this is some label. You're doing, say, mean squared error, something like that, right? And then if you try to compute gradient of this, it will involve all your data points in the definition. And you don't want to do that. So what do? You say, I create a random function where this data point is picked uniformly randomly among all possible options. You're literally picking one of these summands at random. Okay? Why on expectation, this would behave like this one? When you take expectation of this function, what do you get? You go through your randomness and you sum it up, right? So what is our probability here? It is uniform on all these numbers. So that means every number comes out with probability 1 over n. Correct? And if you put those numbers in, multiply it with 1 over n, and sum it through, you'll see you'll get this guy back. Okay. So it's very funny here. Instead of computing the whole thing, you're somehow recording that whole sum in your probability design. I was summing over everything, then I was averaging. Right? Instead of doing that, I'm picking everything with 1/m probability now. And when I take the expectation, it would behave like as if I'm summing. Okay. All right. And then, of course, still we did not prove anything saying, or I did not give you any strong argument saying this is a good idea. On expectation, if you're doing well, how do you actually know when I just take that random thing and keep iterating, I'm actually going to do well, okay? That's a separate thing. I may, as I said, probably next lecture talk about it 10, 15 minutes. But for now, you see probably this satisfies the properties I told you, okay? Another example. This is like, what is it? Support vector machine or something. Let me see. So we got labels and we got data points. And then we would like, yeah, this is support vector machine. Suppose you're trying to classify using like a one hyperplane cut, your data points, plus and minus, you're going to cut them through. Ones here are good, ones here are bad, okay? Something like that. All right. And then this is your A defining that cut. And you want to find the best one. What's the best one? A way to define it is this. You look at your vector, you multiply it with the cut you're trying to design, it gives you a number now. Then you multiply it with the label of your vector, which is either +1 or -1. You're basically penalizing for wrong classification. Okay. If your vector was supposed to be a +1, but your A is giving a negative number here, you will be penalized. If it is going to be -1, if it is giving a positive number, you'll be penalized. Okay. All right. And then usually you would add some regularization term so that your A does not go crazy. So this is like a typical loss function in what's called support vector machines. They are still sometimes used, and probably before we finish the semester, I'll tell you what they are more formally. But this is a standard thing, right? And then what we do, same story. Pick one of those data points randomly and define your function as max of that plus the regularization. Okay. And it again satisfies the properties that we wanted to satisfy, and its gradient is easy to write down. Not super clean, but much easier than computing through all these data points. So this is the idea of stochastic gradient descent. You create something random that imitates the actual thing, but it is much cheaper to compute. All right. And here is one old example. Suppose you would like to compute mean of a whole bunch of numbers, too many of them. You got like 1 million numbers, you'd like to compute the mean. Can we use this stochastic gradient descent for that purpose? What is mean? A description of the mean number is you're trying to, let's say, yi are your data points, and you're trying to find the x that minimizes this loss function. So what is one way to look at mean is as follows. Let me draw you a picture. So imagine your data points are just numbers, okay? They're lying on the line somewhere. And the mean can be described as follows. If you've seen k-means or anything of that sort, you also know this intuitively. Find a dot for me. When I look at pairwise distances and sum them up, that'll be the smallest. So what kind of dot is good? So think about it like physically. You're finding a dot, and from there, suppose you're putting like an elastic band from that dot to your data points. Which dot would be the best to use the least amount of elastic band? You know. So this is the characterization of mean of a sequence of numbers. We talked about this when we were doing probability, but we talked about many things. So if you forgot, very normal, right? So I will use that and do gradient descent. What will I do? Pick one of those data points randomly. Literally, that's going to be your loss. How far are you from that random point? You can compute the gradient right away. And you can run stochastic gradient descent. And you should be very close to the mean in a few steps. Okay. And people apparently have done this in the 50s. Okay. They also thought about like what should be my good learning rate for this stochastic gradient descent. And Robinson and Monroe, back in the day, they pick it as apparently 1/k, roughly speaking. So they changed learning rate depending on the number of steps. They first go like 1, then half, like you first go adventurous, then you start being more conservative. And there's some mathy arguments justifying this is not a bad idea. But at the end, it's almost feels like cheating, right? So I created such an easy function, pick a random point and just measure distance, random point among your data. Just look at how far is your x from that point. Okay, that's all you're doing. And you're updating at every step using gradient of that function. Okay. And you end up proving this is actually not too bad. Okay, very good. Now, I'll tell you the intuition behind this and also a very nice algorithm called randomized Kaczmar's algorithm next time. Now, let me tell you what you would see related to this if you just pull up some modern package you're using, JAX, PyTorch, or TensorFlow, whatnot. So to tell you what you're going to see, we need to establish small vocabulary, which is if you're using gradient or something of that sort, it's called first order algorithm. If you're using second, which is Hessian, it's called second order algorithm. And there are things in between. They are usually called quasi-Newton. So 1, 1.5, 2, okay? So how do they look like? So the first order looks like, typically my dot, then a learning rate, then a gradient, or maybe this is gradient. Stochastic gradient descent will look like a function g, which involves some random stuff here, and it behaves like my gradient. The stuff with 1.5 would look like this, some learning rate here, then a matrix. They would usually write B inverse. And then again, you could do something random, or you could do standard gradient descent. And this B should be easier to compute than Hessian. And the most expensive and the strongest one is Newton's method, which is take the Hessian, second derivative of your function, use its inverse in that spot. This is what Newton invented. And to this day, it's a very good method. Amazing that he was able to do it so many 100 years ago. So this is very expensive. Gradient is cheaper, but it's hard to prove guarantees if your function is not so nice, like the ones we have seen. Usually, you would do something in between, okay? Because the gradient is only using first order, just the first term of Taylor. If you would use the second one as well, try to find the best vector, you will get Newton, okay? Now, let's not use the second term in Taylor. Let's not use Hessian. Let's also not just stop in the gradient, do something in between, okay? So here is one such idea. It's called Ada grad. And let me see. So what I'll tell you today and coming lectures is these 3 algorithms. Let me just open the PyTorch. So this is Ada grad, which you're just about to see. I might come back here after I tell you what that is. Then we will see something called Ada delta. It's an improvement upon Ada grad, but there are some differences. And the other thing I'm going to show you is called RMS prop. So I'll show you these 3 algorithms, which are all quasi-Newton. So we will start from this Ada grad, then move back to Ada delta, then RMS prop. Okay. So let's get back. How does Ada grad look like? So the idea in Ada grad is like We would love to have the Hessian, but it's too expensive to compute. But we keep computing gradients along the way. Maybe accumulate them to get a decent estimate to the Hessian. So what do? You take the gradient, you multiply it with its transpose. When you multiply a vector with its transpose, now you have a matrix, which is positive, semi-definite, and nice, okay? So this thing is now a nice matrix. You keep summing it through as you go. Or probably you should also average. I probably forgot one over here. I'll have to double check. Okay, this I will check. Let me put a question mark, but I think that should be the case. Okay, then now you think this is like a decent estimate to your Hessian. Then you imitate what Newton was doing. Take inverse of that, multiply it with your gradient vector, put a learning rate on top, keep iterating, okay? And of course, this worked out when it came about, quite well in a lot of things that was not going so well for state of the art back in the day. It was not just a theoretical idea. There were experiments, but it doesn't change the fact that this is something expensive to compute. I keep accumulating all these matrices all along, okay? But easier than Hessian, but not so expensive either. For convex functions, there's proven guarantees for this algorithm. And it is also kind of can be made online. So that's a side remark. You could also implement this algorithm on a streaming model. The guys who invented this were, I think, consulting for Google back in the day. They're academics from Princeton. And apparently that's what Google needed for these online auctions. All right. That's Ada-Grad. And a practical variant is like sometimes people just use diagonal matrices instead of this huge thing and create the diagonals off of the norm of the gradient vectors. And let me show you Ada delta. Or maybe I'm in the last minute. So I showed you Ada-Grad. Let me show you in pseudocode, then we can call it a day. So when you look at this, before seeing what I just wrote to you, it might be hard to understand what it is talking about. So here the square root means square root of a matrix. And 1 over square root means inverse of that square root. Okay? So this is a matrix. They keep accumulating the sum of those PSDs as I showed you in the right thing. You accumulate that sum. It's a huge PSD matrix. Every PSD matrix has a square root, Cholesky factorization. Do that, then take the inverse, multiply that inverse with your gradient, put a learning rate in front, that's your update rule. That's Ada-Grad in your PyTorch. And they would usually add a small epsilon here, because if this matrix is going crazy, putting something crazy on the denominator is not a good idea. So you kind of smooth it out by adding some small matrix next to it. Okay, that's all for Ada-Grad and for today. Next time we'll go from Ada delta, RMS prep. Keep going that way. Thank you so much. Take care.